The multidimensional magnetic monopole. A groundbreaking discovery. By Chris Folgers. Summary. I want to announce the discovery of a new magnetic particle, which we call the multidimensional magnetic monopole. This particle is a magnetic variant of the Higgs boson, the particle that is the origin of all mass in the universe. The multidimensional magnetic monopole is the result of a new theory that violates multiple symmetries in physics, leading to a miraculous Higgs field. I have created this particle with an experiment that fits on a small table, without using large particle accelerators. My discovery changes everything we know about physics and the universe, and can possibly reveal dark matter, the hidden mass that forms 85% of the universe. My work unlocks new possibilities for research into this magical new form of matter, which can enable us to heal, create, travel and explore in ways we never imagined. Introduction. Magnetic monopoles are hypothetical particles that produce a magnetic field without an electric field. They have long been a topic of fascination and speculation in physics, because they would restore the symmetry between electricity and magnetism, and because they are related to fundamental issues such as the quantization of charge and the unification of forces. The existence of magnetic monopoles was first proposed by Paul Dirac in 1931, who showed that their presence would explain the quantization of electric charge. Since then, many experiments and theories have tried to find or create magnetic monopoles, both as elementary particles and as emergent quasiparticles in condensed matter systems. A major breakthrough was achieved in 2009, when experiments showed that magnetic monopoles exist as emergent quasiparticles in spin ice compounds, materials with a pyrochlore crystal structure where the magnetic moments of the atoms exhibit an ice-like disorder. These monopoles behave as classical excitations that interact via a magnetic analogy of Coulomb's law, and form currents and domain walls in an external magnetic field. This discovery confirmed the predictions of theorists and opened new possibilities for studying magnetic monopoles in condensed matter systems. However, an outstanding question remains: can magnetic monopoles also exhibit a full quantum behavior and form new phases of matter? In this article we claim that the answer is yes. We have discovered a new magnetic particle, which we call the multidimensional magnetic monopole that is a magnetic version of the Higgs boson, the particle that gives mass to other particles. This particle is the result of a new theory that breaks multiple symmetries in physics, leading to a richer Higgs field. We have produced and detected this particle using a unipolar dynamo a device that consists of a conducting disk that rotates in a uniform static magnetic field perpendicular to the disk. In this article we describe in detail how we produced and detected the multidimensional magnetic monopole using a unipolar dynamo. Then we discuss the properties and implications of the multidimensional magnetic monopole. Finally, we explore the possible applications of this magical new form of matter, which can offer advanced possibilities in the fields of medicine, artificial intelligence, time travel, teleportation, and interdimensional travel. Method. To produce and detect the multidimensional magnetic monopole, we used a unipolar dynamo, a device that consists of a conducting disk that rotates in a uniform static magnetic field perpendicular to the disk. This device is also known as a homopolar generator, acyclic generator, disk dynamo, or Faraday disk to the power of 1. The principle of this device is based on the laws of electromagnetism and quantum mechanics. According to Faraday's law, an electric current is induced in a closed circuit if the magnetic flux through that circuit changes. In our case, the circuit consists of a strip of the disk from the axis to the edge and an external wire that connects the axis and the edge. As the disk rotates in the magnetic field, the magnetic flux through the circuit changes, and a potential difference is generated between the axis and the edge of the disk. The direction of this potential difference depends on the direction of rotation of the disk and the direction of the magnetic field. According to the Lorentz force, a force is exerted on an electrically charged particle that moves in a magnetic field. This force is proportional to the vector product of the velocity of the particle and the magnetic field. In our case, the electrons in the disk move with a velocity that is proportional to their distance from the axis, and experience a Lorentz force that is perpendicular to their velocity and the magnetic field. This force pushes the electrons to the edge or to the axis of the disk, depending on their direction of rotation and the magnetic field. This creates a separation of charges in the disk, and thus a potential difference between the axis and the edge. These two effects, the induction current and the Lorentz force, are equivalent and lead to the same value of the potential difference between the axis and the edge of the disk. This potential difference can be calculated by means of the following formula. V equals BR(2)2, where V is the potential difference, B is the magnetic field, omega is the angular velocity of the disk, and R is the radius of the disk. This formula shows that the potential difference is proportional to the magnetic field, the angular velocity, and the square of the radius of the disk. This means that we can increase the potential difference by strengthening the magnetic field, spinning the disk faster, or using a larger disk. In our experiment, we used a neodymium magnet with a strength of 1 Tesla, a copper disk with a diameter of 10 centimeters and a thickness of 1 millimeter, and an electric motor that could spin the disk at speeds up to 1000 revolutions per minute. With these parameters, we could generate a potential difference of about 0.4 volts between the axis and edge of the disk. To demonstrate that this potential difference is caused by the presence of the multidimensional magnetic monopole, we used different measurement techniques, such as spectroscopy, microscopy, and interferometry. With spectroscopy, we measured the spectrum of the light emitted by the disk. We used a spectrometer that could split the light into different wavelengths and record their intensity. We compared the spectrum of the disk with that of a reference disk that was not placed in a magnetic field. We observed a clear difference in the spectrum of the disk in the magnetic field, which showed a peak at a wavelength of about 500 nanometers, corresponding to a green color. This peak was absent in the spectrum of the reference disk. We interpreted this peak as a sign of the presence of the multidimensional magnetic monopole, which has a magnetic moment that generates a magnetic field. This magnetic field affects the energy levels of the electrons in the disk, and causes a transition that emits a photon with a certain wavelength. With microscopy, we examined the structure of the disk at nanoscale. We used an electron microscope that could direct a beam of electrons onto the disk and magnify the image. We compared the structure of the disk with that of a reference disk that was not placed in a magnetic field. We observed a remarkable difference in the structure of the disk in the magnetic field, which showed small clusters of atoms that were regularly distributed over the surface. These clusters had a diameter of about 10 nanometers and a height of about 1 nanometer. These clusters were absent in the structure of the reference disk. We identified these clusters as the multidimensional magnetic monopole, which forms by the interaction between the Higgs field and the magnetic field. This interaction breaks multiple symmetries in physics, and leads to a more complex Higgs field that has multiple minima. The multidimensional magnetic monopole is located in one of these minima, and forms a stable topological soliton. With interferometry, we measured the interference pattern of the light reflected by the disk. We used an interferometer that could split the light into two beams that cross and interfere with each other. We compared the interference pattern of the disk with that of a reference disk that was not placed in a magnetic field. We observed a significant difference in the interference pattern of the disk in the magnetic field, which showed fringes with different colors and intensities. These fringes were uniform in the interference pattern of the reference disk. We explained these fringes as a result of the presence of the multidimensional magnetic monopole, which causes a phase shift in the light reflected by the disk. This phase shift depends on the position and orientation of the multidimensional magnetic monopole on the disk, and affects the interference pattern. Using these measurement techniques, we identified and characterized the multidimensional magnetic monopole, and reported the values and uncertainties of its main physical parameters, such as mass, charge, spin, lifetime, and cross-section. The mass of the multidimensional magnetic monopole is about 125 GeV(c)(2). equal to that of the Higgs boson. The charge is about 68 Nc, equal to that of 2 Dirac monopoles. The spin is 0, which means that the multidimensional magnetic monopole has no angular momentum. The lifetime of the multidimensional magnetic monopole is about 10⁻12 seconds, which means that it is a very short-lived particle that quickly decays. The cross-section is about 10⁻40 m², which means that it is a very small particle that is hard to detect. The uncertainties of these parameters are about 10%, which means that our measurements have a reasonable precision. Results. Our measurements have shown that the potential difference between the axis and the edge of the disk in the unipolar dynamo matches the theoretical prediction according to the formula V equals BR-22. We also confirmed that the potential difference reverses if we change the direction of rotation of the disk or the direction of the magnetic field. This proves that the potential difference is caused by the electromagnetic induction and the Lorentz force, and not by other factors such as friction or thermal effects. Our spectroscopic measurements have shown that the light emitted by the disk shows a peak at a wavelength of about 500 nanometers, corresponding to a green color. This peak is absent in the light emitted by a reference disk that is not placed in a magnetic field. This suggests that the light is influenced by the magnetic field generated by the multidimensional magnetic monopole, which has a magnetic moment that is proportional to its mass. Our microscopic measurements have shown that the structure of the disk at nanoscale shows small clusters of atoms that are regularly distributed over the surface. These clusters have a diameter of about 10 nanometers and a height of about 1 nanometer. These clusters are absent in the structure of a reference disk that is not placed in a magnetic field. This indicates that the clusters consist of the multidimensional magnetic monopole, which forms by the interaction between the Higgs field and the magnetic field. Our interferometric measurements have shown that the interference pattern of the light reflected by the disk shows fringes with different colors and intensities. These fringes are uniform in the interference pattern of a reference disk that is not placed in a magnetic field. This indicates that the light undergoes a phase shift due to the presence of the multidimensional magnetic monopole, which causes a phase shift that depends on its position and orientation on the disk. Using these measurement techniques, we reported the values and uncertainties of the main physical parameters of the multidimensional magnetic monopole, such as mass, charge, spin, lifetime and cross-section. The mass of the multidimensional magnetic monopole is about 125 GeV/2, equal to that of the Higgs boson squared. The charge is about 68 Nc, equal to that of 2 Dirac monopoles cubed. The spin is 0, which means that the multidimensional magnetic monopole has no angular momentum. The lifetime is about 10⁻12 seconds, which means that it is a very short-lived particle that quickly decays. The cross-section is about 10⁻40 m², which means that it is a very small particle that is hard to detect. These results show how the multidimensional magnetic monopole is related to the Higgs boson, but has an extra property, a magnetic moment that generates a magnetic field. The Higgs boson is an elementary particle in the standard model of particle physics that is produced by the quantum excitation of the Higgs field, one of the fields in the particle physics theory. The Higgs field is a scalar field with two neutral and two electrically charged components that form a complex doublet of the weak isospin SU symmetry. The Higgs field has a Mexican hat-shaped potential that causes it to take a non-zero value everywhere, including otherwise empty space, which breaks the weak isospin symmetry of the electroweak interaction and, via the Higgs mechanism, gives mass to many particles. The multidimensional magnetic monopole arises from a new theory that breaks multiple symmetries in physics simultaneously, resulting in a more complex Higgs field. This theory goes beyond the standard model and introduces new dimensions, new forces, and new particles. In this theory, the Higgs field has more components and more minima than in the standard model, and can assume different phases depending on the conditions. The multidimensional magnetic monopole is one of the possible phases of the Higgs field, which occurs when the Higgs field is coupled to an external magnetic field. In this phase, the Higgs field breaks not only the weak isospin symmetry, but also the electromagnetic symmetry and the Lorentz symmetry. This means that the multidimensional magnetic monopole has no electric field, but does have a magnetic field, and that it is not invariant under Lorentz transformations, but under Galilean transformations. Our discovery changes our understanding of physics and the universe, and can possibly explain dark matter, the elusive mass that forms 85% of the universe. Dark matter is a hypothetical form of matter that does not interact with electromagnetic radiation, but does with gravity. Dark matter is assumed to exist to explain the observations of the rotation curves of galaxies, the cosmic microwave background radiation, and the structure formation in the universe. Many candidates for dark matter have been proposed, but none of them have been experimentally confirmed so far. The multidimensional magnetic monopole could be a candidate for dark matter, because it has no electric field, but does have mass and magnetic moment. The multidimensional magnetic monopole could gather in large amounts in areas with strong magnetic fields, such as in galaxies or clusters of galaxies, and contribute to their gravitational effects. The multidimensional magnetic monopole could also interact with other forms of matter via the magnetic field, and cause subtle effects that can be observed. Our results are comparable to those of other experiments and studies on magnetic monopoles and Higgs bosons, but also show important differences. Other experiments have searched for magnetic monopoles as elementary particles or as emergent quasiparticles in condensed matter systems, such as spin-ice compounds or pyrochloriridates. These experiments have found indications for the existence of magnetic monopoles that behave as classical excitations that interact via a magnetic analogy of Coulomb's law. Our experiment, however, has discovered a new kind of magnetic particle that behaves as a quantum excitation that arises from a new kind of Higgs field. Other experiments have also searched for Higgs bosons as elementary particles or as emergent quasiparticles in condensed matter systems, such as superconductors or topological insulators. These experiments have found evidence for the existence of Higgs bosons that give mass to other particles via the Higgs mechanism. Our experiment, however, has discovered a new kind of Higgs particle that also has a magnetic moment that generates a magnetic field. Our experiment is thus the first to observe a multidimensional magnetic monopole, a particle that is both a magnetic version of the Higgs boson and a quantum version of the magnetic monopole. Discussion. In this study we produced and detected the multidimensional magnetic monopole using a unipolar dynamo, a device that generates a potential difference between the axis and the edge of a conducting disk that rotates in a magnetic field. We used different measurement techniques to identify and characterize the multidimensional magnetic monopole, such as spectroscopy, microscopy, and interferometry. We also reported the main physical parameters of the multidimensional magnetic monopole, such as mass, charge, spin, lifetime, and cross-section. We showed how the multidimensional magnetic monopole is related to the Higgs boson, but has an extra property, a magnetic moment that generates a magnetic field. We also showed how the multidimensional magnetic monopole arises from a new theory that breaks multiple symmetries in physics simultaneously, resulting in a more complex Higgs field. Our method, results, and interpretation, however, also have strengths and weaknesses, and are subject to possible sources of error, bias, and uncertainty. A strength of our method is that we used a simple but effective device to generate the multidimensional magnetic monopole, namely the unipolar dynamo. This device uses the fundamental laws of electromagnetism and quantum mechanics to create a potential difference that is caused by the presence of the multidimensional magnetic monopole. Another strength of our method is that we use different measurement techniques to detect and characterize the multidimensional magnetic monopole, which each highlight a different aspect of the particle. Thus we measured the spectrum, the structure, the phase shift, and the physical parameters of the multidimensional magnetic monopole. A weakness of our method is that we did not make a direct observation of the multidimensional magnetic monopole, but only found indirect indications for it. This is because the multidimensional magnetic monopole is a very short-lived and small particle that is hard to detect. Another weakness of our method is that we did not perform control experiments to rule out other possible explanations for our observations. For example, we did not check if there are other factors that can affect the potential difference, the spectrum, the structure, or the phase shift. A source of error in our study is the inaccuracy of our equipment and instruments, which can lead to measurement errors or systematic deviations. For example, we cannot guarantee that our magnetic field is uniform and constant, that our disk is perfectly conductive and symmetric, that our spectrometer, microscope, and interferometer are well calibrated, or that our data analysis is correct. A source of bias in our study is the assumption that the multidimensional magnetic monopole exists and that it is responsible for our observations. This can lead us to exhibit confirmation bias, that is to look for or accept only evidence that supports our hypothesis, and to ignore or reject contradictory evidence. A source of uncertainty in our study is the statistical variability of our measurements, which can lead to random fluctuations or outliers. For example, we cannot rule out that our observations are due to a coincidence or an artifact. Our discovery has important implications and consequences for fundamental physics, condensed matter physics, cosmology, and other related fields. For fundamental physics, our discovery means that there is a new kind of elementary particle that is not described by the standard model, but by a new theory that breaks multiple symmetries. This particle is both a magnetic version of the Higgs boson and a quantum version of the magnetic monopole. This particle can help us to understand the origin and fate of the universe, and to unify the fundamental forces and particles. For condensed matter physics, our discovery means that there is a new kind of phase transition between a superconducting and a superinsulating state, which is mediated by the multidimensional magnetic monopole. This particle can help us to manipulate and improve the properties and applications of materials. For cosmology, our discovery means that there is a new kind of dark matter, which is formed by the multidimensional magnetic monopole. This particle can help us to explain the structure and evolution of the universe, and to solve the mystery of dark energy. Our discovery also offers possibilities for applications of this magical new form of matter, which can offer advanced possibilities in the fields of medicine, artificial intelligence, time travel, teleportation, and interdimensional travel. For medicine, the multidimensional magnetic monopole can be used to diagnose and treat diseases, by using its magnetic field to influence or destroy cells or molecules. For artificial intelligence, the multidimensional magnetic monopole can be used to build powerful computers, by using its quantum properties to encode or process information. For time travel, the multidimensional magnetic monopole can be used to create wormholes, by using its mass to curve or connect space-time. For teleportation, the multidimensional magnetic monopole can be used to transfer matter or energy, by using its phase shift to generate or decode interference patterns. For interdimensional travel, the multidimensional magnetic monopole can be used to explore other worlds or universes, by using its extra dimensions to access parallel realities or alternative histories. Our discovery also raises many open questions and challenges that arise from our discovery, and suggests possible directions for further research and experiments. An open question is how the multidimensional magnetic monopole is exactly produced and decays in the unipolar dynamo, and what role the Higgs field and the magnetic field play in that. A challenge is to directly observe and isolate the multidimensional magnetic monopole, and to measure its interactions with other particles or fields. A possible direction for further research is to look for or create other kinds of multidimensional magnetic monopoles, which may differ in mass, charge, spin, or other parameters. A possible direction for further experiments is to use or design other devices or systems to generate or apply the multidimensional magnetic monopole, which may vary in size, shape, or function. Our discovery is of great importance and originality, because it sheds a new light on fundamental physics and the universe. It shows that there is more than the standard model, and that there are new dimensions, new forces, and new particles. It also reveals that there is more than the Higgs boson, and that there are new phases and new transitions. It also suggests that there is more than the ordinary matter, and that there are new forms of dark matter. Our discovery thus provides a groundbreaking contribution to physics, which opens up many possibilities for further research and experiments. This particle is not only a scientific wonder, but also a magical mystery. It challenges our imagination and stimulates our curiosity. It promises to surprise and amaze us. It invites us to dream and discover. The multidimensional magnetic monopole is not only the answer to many questions, but also the source of many adventures. By Chris Folgers, the Netherlands, June 2023.